In the last lesson, we learned that time dilation is the apparent slowing of time experienced by a moving object when observed by a fixed observer. We also learned that the fact that the speed of light remains constant for any observer, moving or stationary, contributes to time dilation. In this lesson, we will conduct a mathematical experiment to discover time dilation and derive a formula for how much time has slowed down for objects moving at certain speeds. For our experiment, imagine a clock made from two mirrors with a photon of light bouncing in between them. For our imaginary clock, every tick occurs when the photon travels from one mirror to the other, called delta t. The mirrors are separated by a distance d, and the speed of light is c, constant. If delta t is the amount of time it takes for the light to travel over distance d at speed c, then delta t is equal to d over c. In our experiment, let's then assume that the entire clock is moving relative to the observer at velocity v. The distance between the two mirrors at any time is still d, but now the photon appears to move diagonally since the clock is moving relative to the observer. The length of the diagonal path that the light takes will be called L. The speed at which the whole clock is moving will be called v. Since the mirrors are moving relative to the observers, we need a new variable for the time observed by the non-moving observer, which will be called delta t(O), or delta t observer. The distance that the clock moves in one movement of the photon from one mirror to the other can be expressed by v delta t(O). This is the distance that the clock moves in one tick. We can see that the distance between the mirrors d, the distance that the clock moves, v delta t(O), and the length of the path of the photon L make a right triangle. We can use Pythagorean theorem to create an equation for the distance L. When plugging in, it will look like this. L is equal to the square root of d squared plus v delta t(O) squared. We can also create an equation for the time of each photon movement, t(O), by using the speed of light, which will look like this. Delta t(O) is equal to L over c. So each tick will be equal to L over c. Remember, because the speed of light stays the same for every observer, the c that we use to find delta t(O) is the same c that we use to find delta t when the clock is not moving relative to the observer. Since we have an equation for L, we can substitute it for L in the equation delta t(O) is equal to L over c to end up with this equation for the observed time. Delta t(O) is equal to 1 over c times the square root of d squared plus v delta t(O) squared. This equation gives us delta t(O) in terms of d and v, and fortunately we have an equation that can give us d. By solving the equation for the time per photon movement when the clock is still, delta t is equal to dc, we can get d is equal to c times delta t. Now we can substitute that into our equation for delta t(O). To get the final equation, delta t(O) is equal to 1 over c times the square root of c delta t squared plus v delta t(O) squared. Now that we have our equation for the time for each photon movement of the moving clock as observed by the non-moving observer, all we have to do is simplify and solve for delta t observer. First step is that we need to square both sides of the equation. To get delta t(O) squared is equal to 1 over c squared times c delta t squared plus v delta t(O) squared. Next, we can distribute the c squared term into the term in the parentheses to get delta t(O) squared is equal to delta t squared plus v squared delta t(O) squared over c squared. Next, we move all the terms including delta TO to one side, getting delta TO squared minus v squared delta TO squared over c squared is equal to delta t squared. Next, we can factor out all of the delta TO terms, getting delta TO squared times 1 minus v squared over c squared is equal to delta t squared. Next, we move the 1 minus v squared over c squared term back to the right side, getting delta TL is equal to delta t squared over 1 minus v squared over c squared. Finally, we can apply the square root to both sides, getting our fully simplified equation, delta TO is equal to delta t over the square root of 1 minus v squared over c squared. It's easy at this point to get confused about what this formula means, so let's remind ourselves of the terms. Delta TO is the amount of time it takes for the photon to move from one mirror to the other in the moving clock as observed by a non-moving observer. It's how fast each tick appears to us. Delta T, on the other hand, is how fast the moving clock ticks if it is observed by an observer without a different relative velocity. So if we were moving with the clock, delta T is what the tick speed would seem to be. V is the velocity of the clock relative to the observer. And one of the most important things to notice is that as V increases, the bottom of the fraction gets closer to 0. This increases the value of the whole fraction, which increases the amount of time the clock takes to tick as observed by the non-moving observer. This means that as the relative velocity between the clock and the observer increase, the clock appears to tick more slowly. Each tick takes more time. This phenomenon is called time dilation, and we have just derived its formula using the basic assumption that the speed of light is the same for every observer, no matter their velocity. In the final lesson, we will learn how the phenomenon of time dilation affects nature and our human lives.